Alrighty, let us solve some sequences, solve some convergence or divergence of sequences. This is going to be a follow along type of video, or I'm trying to mimic like office hours kind of as well, or review session, whatever you want to call it as well. I'm taking these problems from the Stewart Calculus textbook, early transcendental version, 7th edition, section 11.1. It's a very common textbook. Okay. So I'm also going to show you how I studied for math. I did the problem, and then for the odd questions, I went to the back of the book to check my answer. If I did not get it right, then I figure out what went wrong. I try to figure out what went wrong, okay? All right, so without further ado, let's begin. Number 23, all these questions are determined whether this sequence converges or diverges. If it converges, find the limit, all right? So number 23, we have a sub n is 1 minus 0.2 to the n power. So does this guy converge? Does it diverge? Go ahead and try it first. In the interest of time, I'm not going to pause every time. Only for this first one, okay? So limit as n goes to infinity of a sub n is the limit as n goes to infinity of 1 minus 0.2 to the n. Let's put this in the square bracket as well, okay? What is this limit? Well, the limit of 1 is just 1, okay, constant. Now what about 0.2 to the n power? When we raise a fraction that's less than 1, absolute value-wise, less than 1, to the n power, so like imagine half to the n power. You keep having something. So it's going to get smaller and smaller and smaller. So it's going to approach 0. Anything bigger than 1, even 1.1, we're growing. In this case, we're growing by 10% every time. So it's going to blow up to infinity, okay? And at 1, it's just a constant 1, okay? So in this case, 0.2 to the n power is going to approach 0 as n keeps getting bigger and bigger. So the final answer is 1. Let's check. That was number 23. 1. Good. 25. How about this one? All right. This one we can eyeball right away. It converges to 5. How do I know that? Well, if this were a function, we know how to do it. For functions, rational functions, what's the quick way to do it? The degree of the top is the same as the degree of the bottom, the biggest power of x. So what do? We take the ratio of the leading coefficient. There's an imaginary 1 there, right? Okay, so that's why it's 5. We can do the exact same thing for a sequence. Okay, so that's why the limit is 5. Or the proper way to do it, to show our work if your instructor requires it, limit as n goes to infinity of 3 plus 5n squared over n plus n squared. How do we do this? We need to factor out the biggest degree on the top and on the bottom. So n squared is the biggest degree on top, so it becomes 3 over n squared plus 5. And then n squared is also on the bottom, the biggest degree, so we get 1 over n plus 1. Okay, these n squareds cancel. Now if we take the limit, 3 over n squared goes to 0. We're left with 5 on top. That's a constant. 1 over n goes to 0. And 1 remains. That's a constant. So this is 5. Same answer. Okay, you should be able to quickly eyeball these rational function looking type sequences. You will need to do them a lot in the future series sections. Okay, what about this one? Limit n goes to infinity, e to the 1 over n. This is a composite function. Imagine it's like e to the x and 1 over x. Remember, for composite functions, we can go find the limit of the innermost first, and then if it's continuous, plug it into the outer one, stuff like that. We can use the exact same things from functions in sequences as well. So as n goes to infinity, what does 1 over n approach? It approaches 0. So the limit is e to the 0, which is 1. We should check our work. 27 is 1. Yep. 25 was 5. Yep, there we go. Okay. 29, what about this guy? This tangent guy. Limit as n goes to infinity. We could actually use the exact same principle we used in the last guy. Tangent 2 pi n over 1 plus 8n. We can first take the limit of the inside of the tangent, the argument of the tangent. Okay, and then let's use the quick way. Degrees are the same because on top is to the first degree, bottom's also to the first degree. Take the ratio of the leading coefficient. So we get 2 pi over 8, which is tangent of pi over 4. What's tangent of pi over 4? It is 1. I saw it was a 1 for number 29. Yep, there's 1. All right. What about this guy? So in this one, we can use the same principle as we did before. Okay? Let me explain and let me show you the long way to do it. Okay. As n approaches infinity, on the denominator, let's look inside the radical. Which term will dominate, the n cubed or the 4n? Clearly, the n cubed will dominate as n keeps getting bigger. So for large n, essentially we have n squared over square root of n cubed, which if we simplify, it's n squared over n to the 3 halves. We can rewrite the radical as an exponent. So we subtract the powers, it's n to the half. And as n approaches infinity, for n to the half, it blows up to infinity. Yeah, so this guy should diverge. Now let's show it the long way. Limit n goes to infinity. We use the exact same technique. Let's factor an n cubed inside the radical. So 1 plus 4 over n squared. Okay, now limit n goes to infinity. N squared over square root of n cubed, square root of 1 plus 4 over n squared. This is by properties of radicals. And let's simplify. As I was saying up here, n squared divided by square root of n cubed, that gives us square root of n on the top, or n to the half. Okay, so the bottom will approach 1, but the top will approach infinity. So this guy diverges. Now check number 31, D diverges. Good. 33, what about this guy? You might have to use one of the theorems that you should have learned. Okay. You got to be careful with the theorem as well. Let me write the theorem. If limit n goes to infinity, absolute value a sub n is equal to 0, then limit as n goes to infinity of just a sub n is 0 as well. Okay? This is the theorem, and you have to be careful. It's when it's 0. It cannot be anything else. Let me give you a counterexample to illustrate the point. Let's say we have a sub n is just negative 1 to the n. So it's going to be negative 1, 1, negative 1, 1, so on and so forth. The sequence, yeah? Okay? If we take the limit as n goes to infinity, absolute value a sub n, this is just 1, because when we absolute value, these become positive, yeah? Let me write the minuses back. But if we take the limit as n goes to infinity of just a sub n, it does not exist because it oscillates between negative 1 and 1. Precisely because it oscillates between negative 1 and 1 doesn't converge to a single number. So it doesn't exist, doesn't converge. Okay? So hopefully I gave you the key idea for why it has to be 0. Because, let me also just explicitly say it, as you decay to 0, even if you alternate signs, hopefully you can see the dots, it approaches 0 as well. If you flip the negatives to a positive, yeah? Kind of hard to see the small dots, but draw it for yourself and convince yourself if otherwise, okay? All right, now let's go back to the actual problem at hand. So this is the theorem that we're going to use. All right, so the theorem is actually very easy to use. So we do the limit n goes to infinity, absolute value a sub n. This is just the limit as n goes to infinity of 1 over 2 square root of n, which is 0. Therefore, limit as n goes to infinity, a sub n without the absolute value is 0 as well by the theorem. Next, by the way, we should check that. It was 0, right? Good. 35. What about this one? So limit n goes to infinity, cosine of n over 2. Well, as n gets bigger and bigger, what happens to cosine? What does cosine of x look like as a function? Cosine x. This is x. It oscillates between -1 and 1, yeah? So even if we divide x or n by 2, I mean, it just stretches it a little bit, right? The period is longer, but it still oscillates between two values. So this guy does not exist, and therefore it diverges. Okay? 35 diverges. Next, what about this guy? We have factorials. What do we do about this? Do we get intimidated? This is actually important for when we learn the ratio test in the future sections. Okay? And parentheses and stuff like that. Okay. So let me explain. Well, what is 5 factorial expanded out? For example, this is 5 times 4 times 3 times 2 times 1. Okay? Wouldn't you agree that 5 factorial is also the same as 5 times 4 factorial? Because 4 factorial is 4 times 3 times 2 times 1. That's right here. This guy right here is 4 factorial. So 5 factorial is 5 times 4 factorial. And if we divide the two, this is 5 times 4 factorial on top and 4 factorial on the bottom. We're left with 5, yeah? So we're going to use this idea, not really an idea, it's just a fact of how factorials work, into this guy. So our a sub n is 2n minus 1 factorial over 2n plus 1 factorial. So which one's bigger, 2n minus 1 or 2n plus 1? 2n plus 1. So we're going to start breaking off some terms. So 2n plus 1 factorial is the same thing as 2n plus 1. Next term, we would subtract 1, so that's 2n. Next term, we would subtract 1, so that's 2n minus 1. Oh, let's leave the factorial there because that's on the top. These cancel, so you're left with 1 over 2n plus 1 times 2n. This is equivalent to the guy we had in the beginning. So the limit as n goes to infinity of a sub n is the same thing as the limit as n goes to infinity, 1 over 2n plus 1 2n, which is equal to 0. The degree on the bottom is bigger. Let's check. This is what? Number 37? 0. Okay. Ooh, what about this exponential guy? Well, if we take the limit as n goes to infinity, e to the n plus e to the minus n over e to 2n minus 1. Well, this is infinity over infinity, so we could use L'Hopital's rule. Let's be very careful, though, because if we keep doing L'Hopital's rule, it's probably going to be endless, because the derivative of an exponential function is an exponential function, so it won't disappear. But this minus 1 will disappear when we differentiate it. So on the bottom, we get 2e to 2n. On the top, we get e to the n minus e to the negative n. Chain rule, don't forget that. Okay. Now, let us rewrite this a little bit. E to the n over 2e to 2n minus e to the negative n over 2e to 2n. I broke up the fraction. So we want to find this limit, or we can simplify a little bit. Limit as n approaches infinity. What is the first guy to simplify to? We could also factor out a half if we really want to. I'm not going to do that here. E to n divided by e to 2n. We subtract the powers. So n minus 2n, that's negative n. So we get 1 over 2e to the n on the bottom. Now what about this second one? We can subtract the powers as well. Negative n minus 2n, that's negative 3n, so that is 1 over 2e to 3n on the bottom. And as n approaches infinity, both terms are 0, so our answer is 0. I believe I saw a bunch of zeros upcoming. Okay. 41, what about this guy? Limit n approaches infinity, n squared e to the minus n equals, in order to use L'Hopital's rule, it has to be 0 over 0 or infinity over infinity. So we can rewrite the negative exponent as a positive, but on the bottom. Now it's infinity over infinity. So we can take the limit as n goes to infinity. Differentiate the top, that's 2n. Differentiate the bottom, that's just e to n. Still infinity over infinity. We can do it once more. So it's 2 on top, e to n on the bottom. This goes to 0. By the way, intuition, this is important, especially when you have to do the comparison test. Look at this term right there, n squared over e to the n. Which term grows faster, a quadratic or exponential function? The exponential function, hopefully you answered. So the bottom will grow faster than the top, meaning you're going to be dividing more, which leads to the 0 answer. What about this one? Cosine squared n over 2 to the n. Okay. Well, the problem is if we take n approaches infinity, what does cosine squared n approach? Does not exist. So we can't use L'Hopital's rule or anything here, but does this limit actually exist? Maybe we can use the squeeze theorem. Remember that guy? Cosine of n. What's the range of cosine of n? Between 1 and negative 1. Okay, so if we do cosine squared n, that is between 0 and 1. Okay, now let's just divide by 2 to the n everywhere. So 0 is less than or equal to cosine squared n over 2 to the n, which is less than or equal to 1 over 2 to the n. Okay, now limit as n goes to infinity. We need to show that the limit of the two ends are the same so that we can squeeze the middle and say that the limit is the same as the two ends. Okay, so the limit as n approaches infinity of 0 is clearly 0, and the limit as n approaches infinity of 1 over 2 to the n, well, as n keeps getting bigger, the exponential will keep getting bigger, and you're dividing by more, so that's 0. Therefore, by the squeeze theorem, limit as n approaches infinity of cosine squared n, I'm squeezing it in because actually, yeah, I'm running out of space on my screen. Cosine squared over n, this is 0 as well. Convergence. Okay. What about this one? Limit n goes to infinity. We should check our work, by the way. Before that, 41 and 43 were both 0. 43 we said was 0 by the squeeze theorem. This one we said was 0 as well by L'Hopital's. Okay, this one, what about this one? N sine of 1 over n. Well, this is infinity times 0. So indeterminate product. Let's make it indeterminate quotient. So we can do sine of 1 over n on top and 1 over n on the bottom. Okay? Now, let's do L'Hopital's rule because now it is 0 over 0. So when we differentiate the top, what do we get? We get cosine of 1 over n. And we need to differentiate the inside, the chain rule. I'm just going to write 1 over n prime because, look, we also have to differentiate that at the bottom. So these cancel, and we're left with limit as n goes to infinity of cosine of 1 over n, which is cosine of, what does 1 over n approach as n approaches infinity? 0. So what's cosine of 0? It is 1. There's our answer, 1. All right. What about this guy? This is a 1 to the infinity indeterminate form. So what do we do for this? Remember, we let y be 1 plus 2 over n to the n power, which means that ln of y is ln of, I'll write the whole thing, 1 plus 2 over n to the n power, which by properties of logs, we can pull that n out in front, so n times ln of 1 plus 2 over n. Okay, now if we take the limit as n approaches infinity of ln y, that is the limit as n approaches infinity of the thing we just wrote, but this is as n approaches infinity, this is 0 times infinity, so let's rewrite it as ln of 1 plus 2 over n over 1 over n. Now this is 0 over 0. We can use L'Hopital's rule. All right, so the top we would get 1 over 1 plus 2 over n. And then we need to differentiate the inside of the log, which is minus 2 over n squared. And on the bottom, we would get minus 1 over n squared. Okay? The two negatives become a positive. These n squareds cancel. So you are left with limit as n approaches infinity, 2 over 1 plus 2 over n. This is equal to 2. We're not done yet because this is the limit for ln of y. We want the limit of y. So limit as n approaches infinity of y, which is our a sub n, is what do we need to do? It's e squared. We got to exponentiate because this was ln y. To get back to y, we got to exponentiate by e squared. That's the limit of this sequence. I believe I saw e squared. Yes. Okay. What about this one? This is a infinity minus infinity. So this is a lot of revealed L'Hopital's rule, as you can see. So limit n approaches infinity, a sub n is equal to, how can we make this indeterminate difference into 0 over 0 or infinity over infinity? We can use properties of logs. ln of a minus b is ln of a over b. Okay? And now we can apply that property where let's take the limit of the inside first. See if it exists. This is 2n squared plus 1 over n squared plus 1. What's the limit of this guy right there? Degrees are the same. Take the ratio of leading coefficients. So it's 2. So our answer is natural log 2. Converges to natural log 2. Let's check. Yep. All right. What about this one? Arctangent of ln of n. So limit n approaches infinity. A sub n is equal to, well, what happens when natural log of n approaches infinity, as n approaches infinity? I cannot speak right now. Okay, so let's break it up into pieces. Okay, let me even draw the block diagram approach that you might have seen me do before if you watched my previous videos. So this is a composite function. Imagine it's a function. So it first goes through the natural log, and then whatever the output of that is, it gets passed into the arctangents. Okay, limits work the same way. I'm going to first find the limit of this piece, and then plug that as the limit, or plug that kind of into the other one. You take the limit as n approaches infinity of the output of the natural log. Okay, so limit as n approaches infinity, natural log n. What is this approach? It approaches infinity. So then the limit as n approaches infinity. Okay, so as n approaches infinity, this guy approaches infinity. So then we pass that into this guy now. That's why if you can even use new letter t, for example, t approaches infinity. I'm just going to use n approaches infinity of arctangent of n. What is this equal to? This is pi over 2. And this is reviewing what we already know from calculating limits of functions. Pi over 2. Yeah? Looks like the last two will be divergence. Okay. Oh, this is for sure a divergent sequence. Why? Well, it never converges to a single value. It alternates between 0 and 1. Never converges to a single value. Okay? What about this one? Why does this one not exist? So this is an important concept to know, actually. The factorial, let me write it, factorial grows faster than the exponential. Exponential. Okay, let's see some values of n. So like when n equals 1, let's compare n factorial and 2 to the n. So let's make a table. Like when n is 1 factorial is 1, 2 to n is 2. When n is 2, what do we get? We get 2 factorial, which is 2. 2 squared is 4. 3 factorial is 6. 2 cubed is 8. 4, when n is 4. At 4 factorial is 24. What's 2 to the 4th power? 16. Oh, look, see? The factorial already outgrew the exponential, 2 to the n. You can see that for 2 to n, you just keep multiplying by 2 to get the next value, yeah? But for n factorial, you're multiplying by a bigger number every time. So the next number would be times 5, next would be times 6, while the exponential is a constant times 2 times 2 times 2. That's why the factorial goes faster than the exponential, and this guy diverges. Okay, again, this is an important concept to know for the ratio test and stuff like that. In the future section, really, it helps you also in comparison tests and all that as well. All right. Okay, hopefully this was helpful. It's kind of a long video, but wanted to do a follow along. I feel like but at this point in calculus, you might have forgotten L'Hopital's rule and all that. So this is a good practice set, actually, even just the odd problems. We got to revisit a lot of techniques to calculate limits.